What is up, everybody? Welcome back to Stewart Science. Today we're talking about force diagrams. So the purpose of a force diagram is to show all the different forces that are acting on an object. So specifically today, we're going to be talking about forces, different kind of forces, and how to represent them for objects that are either moving at a constant speed or not moving at all. So first of all, what is a force? A force is very simply a push or a pull. That's it. A force is a push or a pull. And what causes the push or the pull is what we have to name it. So forces exist as interactions between objects. You have to have two things. One thing causing the force on another thing. And so we call this agent on object, or agent being the thing that does the force, object being the thing that the force is done on. And so you have this kind of like force of something on something. There's two objects involved in all of these names. And so usually we give this a name, F of whatever's doing the force. F, whatever that agent is. So if I punch a wall, like I did when I was in middle school, I punched a wall, you would say F fist. That would be a way to name it. Or you can say F punch or F hand. All those are acceptable. Anything that does the force is what we put in this little lower area here called a subscript. So here's a lot of different kinds of forces. A physical push or a pull. This is any item or any object that's pushing or pulling on something else. I mentioned a second ago, I punched a wall when I was in middle school. That was my hand on the wall, and so that's a physical push or a pull. Or if you're in a car accident, there's the force of a car on your car. And so objects here can do pushes or pulls, and we give those a name by saying F for force in capital, and then whatever object does the force gets written in subscript. So all these other forces down here are specific kinds of forces that we've given specific names to. And there's another video for this coming up right after this one. It's the normal force. That's one. Tension is another name that we give to some things. Friction, drag, and gravity. These are all names that we give to specific kind of forces that are like types of forces. They all fit into these specific groups. And so I'll give you some names for that. So again, the generic one here would be F, and then whatever does the force goes in subscript down there. So whatever object is doing the force to the other thing. So you have this guy punching a punching bag. So if you said F man or F person, that would be correct. F person is another one you can call it. You can say F glove, F hand. If you stick to whatever object is doing the force, that will always be right. Now there are specific categories of forces where the same kind of thing is happening in all of them. So for example, this is a car on a ramp. And so this is what we would call the normal force. This car is sitting on a surface right here, and since that surface is pushing up, that would be F normal. Anytime you have a surface that's pushing, we call that F normal. These are three examples of a wooden plank here that's sitting on a rope, a spring, a bungee cord. All of these are examples of what we call tension. And so if we wanted to name this, we'd call it F tension. Now, if you call this F spring going upward, sure, you can call it that. But the specific general term that we use here for that is tension. Or you want to call this F ropes, you can call it that. That's fine. Or if you want to call this F bungee, that's totally fine. If you want to use the object name instead of tension, go for it. But the general kind of force that we would call this is tension, because all of these involve the stretching of something. Again, just back on this one, if you want to call this F road, pushing up, or F surface, or F, ground, okay, those are all fine. I'll take that. But that specific kind of force where a surface is pushing upward is called F normal. That's our name, normal force. That's caused by the molecules and that individual surface getting squished a little bit close together. So it actually makes the surface bend a little bit to cause that pushback. Okay, so we've got F normal is surfaces. F tension is ropes, springs, bungees, anything that you're stretching out a little bit. If you ever watch a movie and someone, is falling off a cliff and someone grabs them and like grab onto a shirt, like a t-shirt, that would be tension. It'd be the stretching of the shirt that holds it. This one, the box here, is not going anywhere because of friction. So friction keeps the box in place. Even if this is moving here, say he got the box to move, it would still be friction that keeps it from moving at a constant speed. So anything that slows motion, so if the force is this way, his force push, you could say force hands, force person, force push, are pushing this way, friction would be holding it back the other way. So friction, F, friction, is any force that opposes motion. And here we have two examples. If you were just doing the guy, you're looking at the forces on the person who's parachuting. It's the strings that are pulling up on him. That would be F tension. But if you're looking at the whole thing, it's the force of the air on this parachute that slows him down. We call that air resistance is a common name for it. You've probably heard that before, calling it air resistance. But we call that F drag. That's our fancy word for friction that's caused by air. That's the same reason why meteorites burn up in the atmosphere. It's because they're moving so fast that when they hit all those air molecules, it causes so much friction it actually breaks the rocks apart. And so again, you can see here, this guy, he's leaning over a little bit. You can see his hair is getting blown this way. His umbrella is getting blown this way. So there's a force of air acting on him to the right there. And so that would be, again, F drag. That's what we call air resistance. If you want to call it F air, totally fine. Air is the object that does the force. So that's just as good. But our specific name for this general type of force is F drag. So if you saw an airplane that was flying through the air at a constant speed, there's drag that's slowing that airplane down. Or if you've ever been riding in a moving car and you stick your hand out the window, it's drag. It's the air force molecules pushing on your hand that make it get pushed back. And this is, I think, our last specific kind here. This is F gravity, which is another name for this, F gravity. Another name for this is weight. If you're on the earth and gravity's pulling down on you, or anytime the gravity's pulling down, that's the force of the earth on you. So if you want to call it F earth, that's okay. I'll take that. F earth, that's what does the force. So this is all based on gravity, which another name for that is weight. Again, if you want to call it F earth, okay, fine. Call it the force of the earth. But the general name for this kind of force would be gravity. Okay, so let's look at a few specific examples of how we draw this. So if we looked at an object, let's say we're looking at this donkey, for example. We need to think about all the things that are pushing or pulling on that donkey. And so rather than draw a donkey out for our diagram, to keep things simple, our first step when we draw a force diagram is to represent the object as a dot. Some people use a box, but I think a dot is easier. And then we need to draw an arrow every direction that there's a force, and we need to draw the arrow as long as the force is strong. So if you give something a gentle push, make a little tiny arrow. If something's giving a really hard push, make a big arrow. If something has a lot of weight, like an elephant, that downward weight arrow would be huge. But if it was something light like a book or a coffee cup, that down weight arrow would be small. So make our arrow as long as the force is strong. And every arrow that we draw here should represent a push or a pull on the donkey. So if we stop and we think, what are all the things that are pushing or pulling on this donkey? There's a couple that we know of right away. One, the donkey is not in outer space. So there's probably going to be some weight of the donkey. So we're going to say F, gravity. Again, if you want to call it F weight, force weight, that's fine. If you want to call it force of the earth, okay. I like gravity. That's the one I usually use. Now, since the donkey is not accelerating downward and not getting launched upward, we know there has to be an upward arrow that should be about the same length. If my drawing isn't good, that's because I'm bad at drawing. But you should make it obvious. So I try to make it the exact same length. It might be a little bit different, but we're going to say it's the same. And what is keeping this donkey from free falling? Well, the fact that it's on a surface. And if we flip back here, we know that a surface force is called F normal. And again, those two forces, normal and gravity, unless it's going one way or the other and gaining speed one way, it should be the same. So we use these little tick marks to say those are the same strength. Now we also see something else here pulling on the donkey, and that's the rope. Now you have to be careful not to go too far. It's not the guy that's pulling on the donkey, it's the rope, because the rope is what's physically touching the donkey. So don't go too far, because we can get crazy there. Just go to the next thing. What is causing a push or a pull on our object? If our object is the donkey, the rope is pulling the donkey. So we're going to have an arrow here, call it F. You could call it F rope, but remember we gave a special name to that kind of force. If a rope is being stretched, we call it tension, F tension. And then since the donkey's not gaining speed this way, or at least it doesn't look like that from the picture, we need to have an equally long arrow going back this way on the donkey. And what keeps the donkey from going somewhere is friction. So we call this F friction. Okay, and that's our force diagram. There's 4 forces in this case because there's gravity, a surface, tension, friction. And those are all equal. And so we can have a little tick mark here if we wanted to show that those side-to-side forces are the same. Another example here, it's kind of similar. Imagine that this rope is going sideways. I couldn't find any good pictures on the internet. So if we wanted to, we can, do things at an angle. That's a more advanced class. So let's just go straight across here. Let's say she's pulling it straight across. If we want to draw the same forces or the same idea, we start with a dot. And then we have a downward force of gravity. You can say F, I'll mix it up this time. F weight. I usually use F gravity, but if you want to use F weight, go for it. We also have an upward force. Should be about the same. And that's again, F normal. Because the ice is on a surface. Now don't get confused. Sometimes it's not a surface that pushes upward. In that case, you do not call it the normal force. It's only a normal force, F normal, if there's a surface involved. Then again, same as last picture, there's some tension this way, F tension. But unlike the last one, since it's a block of ice, there's no friction back the other way. So you can see here, there's an overall force this way, and we'll talk about that in another video. What this is going to end up causing is a change in velocity that way. Okay, another example. We just had a regular old curling stone sitting there on a surface. We don't have anything pushing it side to side. So for our force diagram, there aren't going to be any side to side arrows unless there's something pushing or pulling it side to side. In this case, there's not. So we still have F gravity, which if you want to, you can call it FG, if you're really feeling lazy. Same thing with the upward arrow. If you want to call it FN for normal, okay. Be lazy. Scientists are lazy. That's it. Ta-da, we're done. There's nothing pushing it or pulling it side to side. So we only have gravity downward, the surface pushing up. That's our only forces in this example. Let's say it was moving at a constant speed. Here's where it gets tricky. Again, always start with as a dot. We still have gravity. And we still have a normal force. So it should be the same length. Now here's the issue. You and many, many other people are going to be tempted to draw an arrow that goes this way because the object is moving that way. The issue is what keeps it going that way? If you answer correctly, you answered inertia. And inertia is not a force. Inertia is the property of objects to keep doing what they've always been doing. If they're at rest, they're going to stay at rest. If they're in motion, they're going to keep that speed unless a force acts. So in this case, moving side to the side, if it's going slow enough and there's no air resistance or anything, it'll keep moving at that speed for a long, long, long time. That's what curling is. So there is no force that goes this way unless there's something pushing it that way. In this case, there's no push or pull that way. Now let's say down the road it gets to a patch of ice that's not as smooth. We're going to see a little bit of friction here. And that's when that block of ice is going to stop. And that's why you see those guys out there when it's curling with the brooms and they're scrubbing away because they're trying to keep it smooth, to keep the rock from slowing down until it gets to the point where they want it to slow down and they let it go. So eventually, a little bit of friction takes over. That's what slows the object down. But while it's in motion, at a constant speed, that's the diagram. There's no arrow here to keep it going because inertia is what does that, and inertia is not a force. All right, one more example. Sorry for the weird diagram. This is the only one I could have that has something in contact here. Let's say this strange roadrunner bird was giving the stone a push, pushed it that way. Now let's draw a force diagram, and what we're going to have is the same two that we usually have. F gravity, F normal, but now we have something else doing the push, and you can call this lots of things. Since it's the object is the bird, you can say the bird's talon, the bird's claw, so whatever you want to call that thing that's doing the force, you can call it that. So F, I would call it bird. If you want to call it F roadrunner, F claw, F hand, maybe an F push, I would take those things. Whatever object does the pushing is what you put there in Subscript. So I call that object a bird, you call it a claw, you say tomato, I say tomato. So in this case, the object would be gaining speed this way. It would be accelerating. Okay, just to recap our essential things here, we start by representing our object as a dot. We have to pick one thing out of the picture that we want to draw a diagram for. And then we need to draw an arrow for every push or pull on that thing. Now remember, you don't need a push or a pull just to stay in motion. Inertia does that, and inertia is not a force. So you only draw an arrow for things that are pushing or pulling on the object. Usually, but not always, gravity or weight is one that you will have to draw in your diagram. And usually to counteract that, there's going to be something going up the other way. If it's on a surface, we call it normal. A lot of times it's hanging from something. We call that tension. And then the last thing to do is give every one of those forces a name. And we have some big categories: gravity, normal, friction, tension, drag. And then if you can't think of it, just call it F for force, and then put whatever object does the pushing in subscript. So that's why this one's F bird. As always, this is Mr. Stewart. Keep learning, no matter what.